different formulas. Remember what we have? We have our formulas where we just were dealing with exponents. We had our formulas where we were dealing with factorial or falling factorial. And remember, with falling factorial, you've got to have those parentheses around it. And we also have the n choose k. And we also had the multi-choose, the n multi-choose k. If you need to type in a formula, and it's pretty common that I would ask you for a question to type in the formula, one of the things that you'll have is you'll have directions on how to type these guys in so that Canvas can grade them. Please note, the first one with an exponent, that's relatively straightforward to type in. Explanation point, relatively easy to type in. But these last three, especially the last two, that's the stacked versions here, the n choose k and the n multi-choose k, these guys, you can't write them in that way. So what I have done in the past is for n choose k, n capital CK, and that's how you can type it in. For the multi-choose, this one, the capital M for multi-choose, that was trying to be a k. And for the other one, the following factorial actually is something that you could type in, but I'll often ask you to type it in either with the standard following factorial symbols, or if you put a capital P there, because that actually is the other symbol for following factorial. Okay. So of those three alternative symbols with the capital P, capital C, and capital M, the capital M one is the only one that I made up. The other two are actually the alternative ways of writing following factorial and combinations. Okay. I don't know how many questions right now. For a paper version final exam, it's typically 6 or 7. I normally times out pretty decently, but that includes all the little subparts that I might have. So in an electronic form, typically it's a little bit more. So I would guess that you're looking at somewhere between 8 and 12 questions, and it's probably going to be right around 10 is my current guess. But again, I haven't written it yet, so I don't know for sure. I should be able to get you those specifications on Monday, because by Monday I should actually have it written, if not fully edited. It's Tuesday now, so Tuesday morning. That's the 23rd. So watch out, we had a change from the registrar on us for our final exam date. So I will probably be sending out multiple announcements about that change in date. It's still the same time. So the time hasn't changed from the very beginning, but the date has changed from the Wednesday the 24th to Tuesday the 23rd. And so I should have all of those dates changed now in Canvas. And what I will most likely be doing, because I've only had this happen to me once before in a summer session when we had a date change on us. Super fun when this happens. Is I will probably be sending you guys out notices. I don't want to say once a day because I don't want to do it once a day, but at least several more times before the day of Tuesday, just so I try to reach all of you and be like, hey, don't forget, it's Tuesday now, okay? So sorry about that, guys. I wish I could have prevented that from happening, but it surprised me as well when it came through this week. I think it came through yesterday. Where were we? Right, counting. So in terms of counting, you've got those main formulas of the exponential format, the factorial or following factorial format, n choose k or n multi-choose k. You want to make sure you remember how to actually calculate all of these different guys. So you want to make sure you know when to use each of these different guys. So the buzzwords that we have with counting are repetition or no repetition, or you can repeat the elements or not. Where repetition is allowed are these first two guys. Where repetition is not allowed is the last two. And remember, repetition we said was the same as building a list or putting things in a row or lining people up in a line or giving them specific job titles. Okay? No repetition is like building a set. So you just throw everybody in as a group. It's like throwing objects in a bag. It's like assigning people to a team, okay, where you're not talking about the team leader at that point. Okay? So this one here writes out the names for all of those guys. Multiplication versus addition. So multiplication is where you're just creating the entire formula. Addition is where you actually have to create your formula in pieces. So you have like a case 1, this is what it looks like, a case 2, this is what it looks like, and then you would add them all together. And we also talked about what happens if we're overcounting or undercounting. So for example, if you overcounted something, this is where you divided by a factorial. If you undercounted something, this is where you multiply by a factorial to put the order back in or to remove the order. Okay? And we actually had back in, I can't remember if it was the last day we talked about counting, but there was a little chart that we had. And I would definitely recommend when you're studying to write that chart down somewhere and fill in the blanks. And this is where repetition, no repetition, order matters, order doesn't matter, and you can actually fill in all of these guys into the appropriate block. It is probably one of the easiest ways to remember all of this stuff as opposed to writing it all out in a list. Okay. Big thing here is make sure that you feel comfortable pulling the details out of a story problem, because for counting questions, you are almost 100% guaranteed that any counting question you have is going to be written in a paragraph form. For example, what are some of the ones that we looked at before? One of our examples that's popping into my head is kids in a classroom setting. There's your context, your story problem. We talked about one of them where we were purchasing something from a store. There's your context. Please note when you're in a story problem you have to read that context to figure out if you're going to have the objects repeated. So for example, if you're dealing with individual people, don't repeat your individual people if you're lining them up in a row. And you're going to need to check to see if the order matters or not. So if you're queuing up the people, putting them in a line, the order would matter. But if you're just putting the people into some sort of team, sports, work, whatever, the order in that case probably doesn't matter unless in that team you have positions. So for example, my head is popping to baseball right now for some reason. If you are assigning your people to not just the team, but also what position they're going to play in that team, that is when the order would matter, because it would matter if person X is assigned to play first base versus second base. That would be a different team formation. Okay? So the context, the story problem here is actually going to tell you which of these formulas that you would get. Okay? So be prepared that it's probably going to be a story problem question. So that would be counting. Oh, the other thing with counting is pigeonhole principle, but because pigeonhole principle is in your book in Chapter 5, I put it down with the Chapter 5 topics. Technically, I probably should have put it back up there. With relations, we did a fair amount with relations, but this here is specifically the intro stuff to relations before we got into either functions or posets. So you need to know what a relation is. Specifically, if you're looking at a relation, we are looking at the ordered pairs. So this is somebody who is a subset of a cross product. So if somebody says, hey, here's the diagram of the relation, give me what the relation actually is, it would expect you to write out the ordered pairs associated with that relation. Well, that's pretty common for me to do on paper. Realistically, on Canvas, if Canvas is going to grade it, it is a pain in the butt to write all those ordered pairs. So it may be something a little bit more simpler that says, hey, which of these ordered pairs would actually be in the relation, as opposed to you writing out all the ordered pairs. Okay. So formatting of some of how I would write the questions changes up if Canvas grades it. You might be asked to build a new relation from older relations. So maybe you have some relation R and you're asked to find the inverse relation or the complement relation, the union, the intersection. This is composition, and that's done the same way as what we did with functions. Realistically, you're not going to have this composition because we'll have the permutation functions. This one here, you may or may not get a question for this in terms of when I'm editing it, especially editing for time to make sure you can complete it in a timely fashion. This here would be one of those questions that would be first to be cut. You're pretty much guaranteed to have a question that gives you a relation either as ordered pairs or as a diagram, as a picture, or as a matrix, and asks you, hey, is this relation reflexive, irreflexive, symmetric, asymmetric, anti-symmetric, or transitive? If you guys did the homework that was associated with relations, the one that was a PDF that you had to print out and write on. Remember, there was there only 3 questions? I think there was only 3 questions, but a bazillion parts on each one. One of the things it had you do was transform the given format that the relation was presented to you and turn it into the ordered pairs or the digraph or the matrix, whatever was not given. But what it also had was check out all these properties. That PDF is extraordinarily similar to what I would give you on a test. It's actually one of the reasons that I typed it up, was because that format of how those questions were worded is how I normally word tests for that section. Now, to be fair, that's what you would see if it's a paper version of the test. It will get changed a little bit in terms of an online version of the test. Okay? Other thing that you're pretty much definitely going to be asked about is identifying whether a given relation is an equivalence relation. Also, you'll probably be asked to identify if a given relation is a partial order, but that would likely be down when we're talking about a Posets question. And if it's an equivalence relation, you would be asked to find A mod R, and the cardinality of A mod R. This is the one that's the list of all of your equivalence classes. So make sure you can be able to find your equivalence classes. So be able to calculate any equivalence class. And let me actually just give you the formula for that. For any element in your building set. So remember, your equivalence class is all of the guys that A is mapped to, if we use function terminology. So if you look at all your ordered pairs, A would be the first one in the ordered pair, and the set here is all the elements for your building set that are actually in the second position of the ordered pair. Or if you're in the digraph, you look at vertex A, and the set here is all of the guys that are at the other end of your arrow. Cardinality, remember, is the distinct equivalence classes. You have to be able to compute the equivalence classes to see which ones are the same, and you almost always have some of them that are the same. Make sure you can find a path or a cycle. One of the things that I'll often do is say, hey, here's a digraph representation of a matrix. Go find a path of length 2. If it's in a Canvas format, it's more of a multiple choice question. It'd be something like, which of the following are a path of length 2 in this particular relation? Also make sure that you can calculate the digraph of a relation or the matrix associated with the relation. If I asked you to calculate the digraph of a matrix of a relation, this would be one that would need to be a file upload, because I don't have a good way for you to draw it. Unless it's a multiple choice question, it just says which of the following is the digraph of this particular relation. So that's something you might see. In terms of the matrix here, this one also could be something like a multiple choice. It says which of the following is the matrix associated with your relation, but it also could be something where you just fill in a couple of the entries in that matrix with your ones or zeros, because remember, this was a Boolean matrix. Okay. So that would be the things that you could look at with relations. The big things are identify properties, identify if it's equivalence relation, be able to write it in the different formats, and be able to calculate off equivalence relations your A mod R stuff. Now, often, if this was paper, I'd put it in one relation at the beginning, so it's just one relation you're given. In terms of an online format, this guy would probably be broken up into multiple different questions that you would see, which means you might have multiple different relations that you're looking at. All right, so in terms of whether the final exam is cumulative or not, this guy here is really the one guy where it would be pseudo-cumulative, and that's because when we were at the midterm, we didn't actually get far enough in induction for me to be comfortable giving you the strong induction on the midterm. So what is likely to happen is you're likely to happen some sort of 2-part question, where the first part deals with a sequence, and in terms of the things that we've done with sequence, we've done advanced versions of sequence, which is be able to find from its recursive formula its closed formula. And we only did order 2. Okay. So this is where we use the characteristic equation, we found the roots of our characteristic equation, and we put it into the two formats of either we had a repeated root or non-repeated root, and those two formulas were as follows. We had u times r1 to the n, v times r2 to the n, and then if it was repeated, u times r1 to the n plus vn, same root, raised to the n. Okay? So one question would be asking you to do this type thing, and it would walk you through it. The first thing would be something like, hey, what's your characteristic equation? Write it out. Then it might be something like, all right, what are your roots of your characteristic equation? Write it out. What's the format that you're going to put your final answer in? Write it out. And then what are your u and your v's? Okay? You had several questions like this when you're back in homework and or a quiz in this section. Now, here's where induction comes in. Induction may be based off of that same question or maybe a different question. And it would say, hey, all right, you've got this formula that we built for this sequence. Prove by induction that this formula actually is the right formula for your sequence. Okay? So in terms of what I'm expecting to give for you guys, it will most likely be a strong induction question, and it will most likely be where you confirm that the formula that was built for your sequence really, truly is the closed formula for your sequence. Okay. And I believe we had some sample questions of this one already available previously. If not, I'll go back and find one for you, because I know that especially with induction, seeing how it could be worded previously is extraordinarily useful. Okay. So that would be the pseudo-cumulative part here. Please note, though, all of the topics that we've done are build on each other. So if you've forgotten a topic from previously, some of them would be fine to forget and you'd still get through the final just fine, but some of them, especially things like sets, if you forget them, it's going to be difficult to get through the final. Well, I mean, you can still do it, it's just more difficult. In terms of functions, here's where I put the pigeonhole principle, and I put some sample questions for the pigeonhole principle at the end of this page. In terms of functions, you may be asked something about domain or range. You may be asked something about one-to-one and onto, but these would be like a second-tier question if we run out of time or it gets to be too long. These are the ones that would get cut off immediately. In terms of how they would be answered or how they would be worded, they could very well be worded just as multiple choice. Which of the following questions is which of the following functions is one-to-one? Which of the following functions is onto? Which of the following functions is bijection? Or it might be something like a drop-down menu. Here's a function. Is it one-to-one? Yes or no. Here's the same function. Is it onto? Yes or no. Here's the same function. Is it a bijection? Yes or no. So it might be something like that. Okay? But in terms of something you'll definitely expect to get something like the pigeonhole principle. Pigeonhole principle, if you get it, it's probably going to be something like multiple choice. But definitely expect one of these permutation function guys, and like you guys requested earlier, is I'll go and put a sample question up of how you could see about your permutation functions. So it would be given to you, typically I give it to you in a 2-row format, and then ask you to write the permutation function as a product of disjoint cycles. Then I might ask you to do some sort of operation on your permutation function. So maybe find the inverse, maybe square it, maybe find the product or really the composition of two different permutation functions. Maybe ask you to do something like, hey, write this guy as a product of transpositions and determine whether it's odd or even. Maybe something similar to what we did previously of, hey, can we find a value of k where p to the k is our identity function. Okay. It is possible you would be asked all of these things. When I do this on a paper test, I'll often ask all of these things, and it's one question but one full page where it's got a bunch of different parts. For us on an online format, it might be something similar where it does have a bunch of different parts, or it might be that I just focus on a couple of these individual parts a little bit more frequently, or a little bit more and leave off the other ones. But I would definitely recommend to be comfortable with answering any of these type of questions. In terms of Posets, we've talked about, up through yesterday, we talked about the topics down to that blue line. So with Posets, definition of what a poset is. It's a set in conjunction with a partial order on that set. Know how to make the Hasse diagram of the poset. In terms of this one, if I actually asked you to draw out the Hasse diagram, it would have to be a file upload. So if I don't do any file upload questions, it would typically be a multiple choice where you identify which of the pictures is the Hasse diagram associated to this poset. Okay? So that's a pretty common one that you would see. Make sure that you can identify if two posets are isomorphic. Remember, that means their pictures are the same. So for example, what might happen is you might be given one of the, well, you'd actually have to be given both of them. But you might be something, maybe it's a multiple choice question as well. Maybe you're given one of the posets. Maybe you're also given the Hasse diagram of one of the posets. And then for the multiple choice, say, hey, which of the following posets is this original poset isomorphic to? Or maybe it would be in the multiple choice, you have the Hasse diagrams of those posets, and you would have to create the Hasse diagram of the one poset that you're trying to see as isomorphic to those other options. Okay? So there's some possibilities here of how that could be worded. In terms of maximum, minimal, greatest, least elements, this would be similar to what we did last time. So if you're given a question like this, you would be given the graph, and you'd be asked to identify who are the maximal or minimal elements, and you'd write them out, you'd list them out. Who are the greatest or the least elements, and you'd list them out if applicable. Okay. And then the last bit here is what we'll cover today, which is dealing with lattices and Boolean algebras. And if we don't get to all of these things, I'll go back and cross off the stuff we don't get to. Okay. But in terms of overarching things, these would be the overarching things to look at. So let me zoom out here. And then in terms of sample questions, I gave us some sample questions here. And I'll go and also, they're not all visible right now, but I'll go and build out some of the missing sample questions that are on a Canvas format as well. But you should definitely expect a couple of questions on posets. Normally, it would be 1 or 2 questions in the paper version, but for us, it's probably going to be split up to a couple more of them just because so it's not humongously long questions each time, so individual little pieces and parts. Definitely expect a couple of questions on a permutation functions. Maybe it's one huge question where you fill in a bunch of blanks, but if I start doing some multiple choice type questions, they would have to be broken up into a couple of smaller questions. You're probably going to get one question on the pigeonhole principle, and it would either be multiple choice or a fill in the blank type thing. In terms of sequences, you would get 1, maybe 2 sequence questions, but typically I only do 1. In terms of an induction question, you're looking at 1 induction question, possibly 2, but realistically just 1. In terms of relations, I don't know how many. For this one here, you're looking at probably 1 question that deals with the equivalence relations and setting this up, 1 question that deals with reflexive, so you're looking probably at 2 to 4 questions, depending how I split those questions up. In terms of counting, you're probably going to see a couple of different counting questions to focus in on some of these different techniques. So because we have 4 different techniques here, it's pretty likely that you'll have at least 4 different counting questions. And it's in terms of sets, you might get 1 question on a set, but likely not. Likely you're going to get the couple counting questions, couple relation questions, 1 induction question, 1 sequence question, 1 pigeonhole question, couple permutation questions, and a couple poset questions. Okay. So that would be overarching what you could expect to see. And like I said, I'll get some sample questions up for these guys. What I'll do is, if we already have the sample questions up in the quizzes that we've had already, I'll just reference which quiz they are. And if we've got some of these that I know already are not up in sample questions, I'll go and fill them in for us. Okay. So any questions from you guys? All right, I'm not seeing any questions come in. So in that case, the next thing on the agenda for today was to look at our activity, and then after we do our activity, then we're going to jump back to dealing with lattices. So what I want to do is give you a quick running head start. Let me stop sharing that. To remind ourselves of where we're at with posets. So this is what we talked about at the beginning of last time. Posets are a set together with some partial order on that set. And the partial order, remember, is reflexive, antisymmetric, and transitive. Our activity is going to be building Hasse diagrams. So remember the thing with building Hasse diagrams. Building Hasse diagrams, you can do it in two different ways. One way is you actually build your digraph of the relation of the partial order, and then you remove extra things you don't need. You make sure that you remove all the loops because you'll never have any loops in your actual Hasse diagram. You make sure there are no transitive edges, so if you have any transitive edges, these are the red things that take a path of length 2 or longer and make it a shortcut. They get removed. And all of your arrows that you have in your digraph get pointed in an upwards direction. So right now in this little picture, this little diagram, they're pointed sideways. That's not okay. You'd have to reorient and make B and C go above A. And all of your directed edges, all of those arrows get converted into undirected edges. In other words, the arrows get converted into just line segments. Okay? Now, one of the things that we did yesterday was we said you can always start with the digraph and do this adjustment, or you can be strategic about building your Hasse diagram to start with, and in that case, what do? You go and you automatically never put in the loops, and you never put in your transitive edges. If you started to put in an edge and it was one of those transitive edges, you quickly erase it. And you automatically make it so these guys are pointed in an upwards direction. Okay? So that's the recap of creating Hasse diagrams and what the posets in partial order are. So at this point, I'm going to throw you guys to activity 11. So activity 11, all of the directions that you will need are actually over on the Zyboard location. I'm right here copying the direct link for you guys in the chat. There's the direct link to it. The thing I couldn't get to work yesterday because my keyboard died on me in the middle of class yesterday. You can join that thing. You should be able to just follow that link directly. It may ask you to log in, and you can totally just log in your UNCC login or otherwise if you want to. What you'll notice when you log in over there is you should see, you may have to zoom out depending on what your automatic settings are, but you should see 5 boxes that say groups 1 through 4 and then little sticky notes that give you directions. Each group has a different direction. You have a different poset that you're going to be asked to create the Hasse diagram of. Okay? So what will happen is I'm going to throw you guys into breakout sessions. You will be automatically thrown into your different groups. You should have had 3 people in each group, but somebody just dropped out of the session here, so you'll have 2 or 3 people in each group. Sorry about that group that's going to have 2 people in it, unless the person who dropped comes back real quick. So first thing is it's going to ask you to draw the Hasse diagram of your poset, and then the second question, it's going to ask you to go and look at what everybody else did, and this is why we're on the Zyboard situation as opposed to just being inside of breakout sessions. And it's going to say, hey, is your Hasse diagram, or really is your poset, isomorphic to anybody else's? Okay. So those are the 2 things that you're going to be asked to do is create your own Hasse diagram for your own poset and then check to see if it's isomorphic to anybody else. Okay? And the answer is yes and no, depending on which group you're actually in. Okay? So before we get started, any questions from you guys? So we want to talk about lattices and Boolean algebras. Boolean algebras are a very specific type of lattice, but you actually don't need to know what a lattice is to talk about a Boolean algebra. So I'm going to talk about the Boolean algebra first to get it out of the way, because literally everything you can currently see is pretty much everything I'm planning on talking about with respect to Boolean algebras, and then we'll go back and figure out specifically what the lattices were. Okay? So Boolean algebra is a special type of lattice. Again, we'll talk about what a lattice is in just a second. And it corresponds, or it is, the poset of the appropriate format. The format goes as follows. This first part right here tells you that your building set is always some power set. So it's a power set of the numbers 1 through 3. And remember what that meant. That means that you are what? You are all the subsets of some set 1 through n. Okay? So 1, 2, 3 up to n. Now, in terms of the partial order, it's ordered by subset inclusion. So what that means is two subsets are considered related if one is a subset of the other subset. Okay? Notice we've actually already dealt with these guys in the examples that we had yesterday, and what one of you guys or two of you guys actually had just a second ago. You had Hasse diagrams that look like this, that actually looked like this square on point or diamond shaped, or this sort of, if you squint at it and think of it as a 3D picture, what looks like a 3D cube. If you put the Hasse diagrams and the vertices together in the correct way, all of these Boolean algebras actually look like n-dimensional cubes. 3-dimensional cube, this one actually comes from, and let me make this a little bit bigger for us. Notice this is n equals 3 right there. Let me see if I can't make it even bigger. Oh, I can't get it super big. All right, n equals 3 right there. So this one here is our Boolean algebra when n equals 3. It looks like a 3-dimensional cube. N equals 2 is our Boolean algebra when n equals cube. This is a 2-dimensional cube, otherwise known as a square. Although technically it's on point here just because of how the Hasse diagram works. N equals 1, or the Boolean algebra when n equals 1. This is a 1-dimensional square, otherwise known as a line. And n equals 0, or b sub 0, Boolean algebra on 0, is a single vertex or a 0-dimensional cube. If we went to n equals 4, which I'm not going to draw over here, you would just get what looks like a mess, but actually would correspond to a 4-dimensional cube if such a thing could actually exist. And in math and other places, we actually deal with these higher dimensional stuff that we can't really touch, so we have ways of representing them as pictures, even though that looks crazy and snarly. Okay? Now, one of the reasons why I wanted to make sure to talk about Boolean algebras, even though they're skirting right at the very end of our class, is because these guys are highly used with respect to computers. Okay? One of the claims to fame with a Boolean algebra is they are often used, or I'll just go with often used, where all of their vertices are labeled with, instead of the mathematical format of saying we're looking at subsets of the numbers 1 through n, they're typically labeled with binary strings. Now remember, we've done something in the past with binary strings as relating to sets. Remember what we've done? We encoded our sets as binary strings. Well, these binary strings of length n would be the characteristic functions encoding of all of the subsets of the big set 1 through n. So for example, and I'm going to be lazy over here, if we focus in on B2, and let me put the labels in red here so it's easy to see, we're looking at our building set A would be just the numbers 1, 2. On the bottom here, you would have the empty set. Well, the empty set means you use none of those 2 elements, so this would be the binary string 0, 0. Now, go 1 up. What happens at this next level, this is the individual set that's just a 1-element set 1 or the 1-element set 2. So in the binary string encoding, you have 1, 1 and 1, 0, and notice that totally corresponds to who? That totally corresponds to your single individual your subsets of cardinality 1, like what we talked about last time. Then the top element of this Boolean algebra is the entire set A. Well, if we encode this with our characteristic function, our 1s and 0s, our Boolean string, this would be 1, 1, and that would be the total set A. Then over here, if we look at B1, you're only looking at your building set of the single number 1. So this guy the empty set would be encoded by a 0, the full set would be encoded with a 1. B0, your building set is the empty set. So you only have the empty set. So for this one here, you don't really label it. But you can, and if you wanted to label it, you could actually pick probably a 0. Over here, if you did your length 3 binary strings, your empty set is always at the bottom. The full set is always at the top, so that's all ones. Then one level up from the bottom or the empty set is one element subsets. In other words, cardinality 1 subsets. So this is where you have 1, 1, and 2 zeros. And one level up is where you have cardinality 2 subsets. So this is 1, 0, and 2 ones. Now, notice what happens, though. When you go up, this guy in the middle at level 2 here is what? It's got to include both the element that was tagged by 1, 0, 0 and 0, 0, 1. So in terms of the binary string, it would be 1, 0, 1. You merge these two guys together, or if you prefer, you add them together. This guy over here would be, well, we've got 1, 0, 0 and 0, 1, 0. When you merge those or add them together, you would get 1, 1, 0. And last one would, anybody have a guess what the last length 3 binary string would be? Throw that to you guys. It should have 2 1s and a 0. Perfect. So 0, 1, 1. So notice one of the nice things about the Boolean algebra is it's actually a way where you can list out all of your binary strings of a certain length. And in terms of these edges, notice what happens. Each edge here is where you differ in terms of your binary string by exactly 1 digit. And what that does is that's a precursor to all sorts of things, including things like grade codes. And if you've never dealt with a grade code before and you are either a computer scientist or computer engineering, which is the majority of us, you're probably going to get to at some point in your academic career. If you've already dealt with grade codes, you've probably already seen these. Okay? But they are very much a thing that we use to deal with all sorts of stuff, including binary strings. Okay? But that's the tie-in with computers and these posets and lattices of why we were dealing with them. Now, here's a fun fact. When you're dealing with your Boolean algebra, it turns out there's a couple of properties that are automatic, and you can see them both when you look at the vertices with respect to binary strings or just in general. Well, if you're going up, so that you could say it's or. I think of it as adding just because it's binary arithmetic. But yeah, the plus in terms of binary arithmetic would be exactly the same thing as if you're dealing with the logical operation or. Yeah. I think I answered your question, but it's all about whether you're going up or down the graph. So like if you're going down the graph, it would be like the logical and, or it would be like, it's not adding in that case. So if you go down the graph, it's different. It's logical and, if you will. Yeah. All right, so a couple of things. First of all, these Boolean algebras are lattices. Again, we didn't define lattices yet, but we will in just a second. And the other thing is the number of elements in your set. Your power set is always 2 to the n. We know that from being a power set, and we also can see that from being binary strings of length n, because why each position has 2 options, 1 or 0. Now, here's some additional facts. One of the things that we do a lot, or that I've done a lot, and we're going to continue to do a lot when we're dealing specifically with lattices as opposed to Boolean lattices, is we deal with this guy D with a subscript, like those guys that you were dealing with in the activity, okay? And remember what that was. This was you take n, whatever n was some number, you take all the positive divisors of n, and then you order it. Your relation deals with, so this is divisors of n is your building set, and it's ordered by division. That was trying to be the division symbol. It failed spectacularly, so perhaps we ignore the red part. And so you order it by who's a factor of who. Well, it turns out if n is a product of distinct primes, and remember what distinct means? Distinct here means that they're all different. So that means you don't have any exponents up here. then your divisor poset, this D with a subscript poset, turns out to be a Boolean algebra, and it turns out to always be isomorphic to, let me find it, black, isomorphic to the Boolean algebra B with a subscript K. Now notice where that K comes from. That K on the subscript tells you how many distinct primes you have. So we could go back and actually add in and say we have K different distinct primes is what those symbols all mean mathematically. So let us look at an example. Actually, let me throw the example to you, and then we'll look at some of the examples. So I went ahead and put together a poll everywhere question for you guys. I'm going to share it so you guys can see it. I know the screens are about to get super duper tiny. And the question here is, all right, you've got a couple of different of these posets. They're the D posets, the divisor posets with an appropriate or different numbers on the bottom, 6, 8, 12, 15, and 30. The question here is, are any of these guys also Boolean algebras? So what do you guys think? Are any of those guys also Boolean algebras? And I'm going to cap it at 5 times because there's 5 possible answers there. Just because when I have forgotten to cap the answers, sometimes I'll get in a class size this size like, oh, I don't even know. I got one time 1,000 different answers. And I was like, how in the world did you guys answer 1,000 different times? So you can answer as many of those guys as you want. So definitely don't think of it as a multiple choice question, more of a select all that apply question. And it is the same location with poll everywhere that we have had the entire time. This is likely to be our last poll everywhere question, unless I pull one for Monday. Okay. Hint, there is more than one of those that is actually going to be isomorphic to a Boolean algebra, or is a Boolean algebra. Now what we're going to do together after the answers start stabilizing, of you guys thinking you got your guesses, is we'll see which Boolean algebra those guys are isomorphic to. So that's the extra thing we're about to do. Huh. Your answers are all over the place. So let me actually get you a little bit of information here. So I was planning on just looking at 3 out of those 4 guys. But let me focus in on 12 first, just based on what answers you guys have been currently selecting. So if we look at the divisor poset, when n equals 12, we say n equals 12. According to this theorem, you have to find the prime factorization of 12. I'm assuming you're all comfortable with that. And once you have the prime factorization of whatever that n is, whatever that number is on the bottom, or in that subscript, you then check to see if the prime factorization has all different primes. And it has to be all different primes of exponent 1, okay? So, for example, here with 12, I can write out my prime factorization, 2, 2, 3, but the 2's are repeated. That means they're not distinct. They're not different. And what that tells you is D12. I'm not sure why I put a little thing on top of the 1 for D12. That actually was very disturbing in retrospect. D12 is not a Boolean algebra. And some people always capitalize Boolean and some people don't in terms of Boolean algebras. Technically, it is the name, but it doesn't always happen. Okay? So that would be how you would determine if somebody is a Boolean algebra or not. Okay? So does that change how you make your guesses? Hopefully it helps. But you would do that same exact technique on all of these guys. You take all of those subscript numbers, write them out as their prime factorization. If you have any primes that repeat in the prime factorization, that would mean it is not a Boolean algebra. There should be, if I remember correctly here, yeah, there's exactly 3 of them should be Boolean algebras, if that helps. All right, well, the guesses were a little bit better, so let us actually check to see how you would find which Boolean algebra you're isomorphic to, okay? So I'm going to skip out on the 1-digit posets here. I'll let you guys handle dealing with them, but I'm going to look at the last 3 posets. So D12, D15, and D30. We just showed that D12 is not a Boolean algebra because 12 has a repeated prime. It's got 2 copies of 2 in the prime factorization of 12. Now, if we look at D15, 15, its prime factorization is 3 times 5. So that tells you 3 and 5 are different. That tells you this guy is a Boolean algebra. But it's also going to tell you which Boolean algebra it's isomorphic to. Notice we have a grand total of 2 distinct primes. So this means that this guy is isomorphic to B2. And if you actually drew the Hasse diagram out of D15, what you would see is the Hasse diagram of both D15 and B2 would look like that little diamond-shaped guy. Okay? Now, what happens if we look at the last one, D30? So you do the exact same thing, so 2 primes. So with D30, we have n equals 30. When we do the prime factorization of 30, 30 is what? 6 times 5. 6 is 2 times 3, so we have 2 times 3 times 5. Notice here, we have 3 primes. Those 3 primes are all different. So that means it is going to be a Boolean algebra. Did not mean to write B yet. So specifically, it's a Boolean algebra, and which Boolean algebra it is based on the number of distinct primes. So here, this would be B3. And if you drew out B3, it would look like the pre-drawn one right up here that looks like that cube, which is similar to, I think, 2 of you guys actually had somebody that was isomorphic to B3 in our activity. Okay? Make sense in terms of how to deal with this theorem. Notice this theorem is really nice in terms of figuring out what the Hasse diagram of D with a certain subscript is, and since these are super common posets, actually they're super common lattices, this is a very handy little theorem. Okay. All right, so let us now go back and talk about lattices. So the thing with lattices is we're only going to get the definition, so all the examples will be next time. All right, so definition of a lattice, it is a poset, so you've got your building set. With lattices, you typically use L instead of A, but you can still use the same building set A. And you have here R, your relation, where every subset or every pair from your building set L has both a meet and a join. Well, this, of course, begs the question of what's a meet and what's a join, okay? So we're going to need to define both a meet and a join. So a meet is considered the greatest lower bound of both A and B. And what a greatest lower bound means is it's easiest to see it in terms of a picture. Okay? So in the Hasse diagram, if you're looking at A and you're looking at B, the greatest lower bound is if you read down the Hasse diagram, you read down to whoever the meet is. So this is their meet with our symbol. The symbol for meet totally looks like a logical and. It also looks like a pointified, I realize that's not really a word, pointified version of intersection, okay? So the meet is below, and the greatest lower bound means it's the biggest guy below your number, your two elements you care about. It can totally be one of the two elements. So the other way of seeing this guy, come down, is it can actually also be this. In this case, that guy would be your meet because it's the one below, okay? Now, your join is exactly the opposite. The join is the least upper bound. And so the least upper bound means we are going to be above A and B. And it's the first one you come to above A and B. In terms of symbols, this guy totally looks like a union symbol, except it is pointified. It's actually a V. Okay. And if the two elements are stacked on top of each other, the join is going to be that top element. Please note, in terms of these guys, one of the reasons it looks so similar to unions and intersections, I'm sure, is a throwback to the fact of we have our Boolean algebras where you go down and you're dealing with the intersections of your sets. You go up, you're dealing with the unions of your sets. Or in terms of the binary strings, you actually are looking at your logical ands and ors as you go up and down your Boolean algebra. Okay? So that's it. That's the definition of a lattice. It turns out with your lattices, you'll automatically always have a greatest element and a least element, your maximum element, your minimum element, those guys with the little, so actually let me write this to the side. Lattices always have a greatest and a least element. And that's just because they have to have all of their meets and joins, which means you're never going to be able to have more than one maximal element, more than one minimal element, which means you always have those two guys, at least in finite lattices. Okay, so that gets you the definition of what lattices are. Next time, we'll look at some examples. All of the posets that we've seen that are D with some subscript or the Boolean algebras we just talked about, all of those guys are actually lattices. And in fact, except for the couple of examples that we had when we had multiple maximal or minimal elements at the end of class last time, all of the examples we've had so far have actually been lattices. But next time we'll start off, we'll do a couple of extra examples of lattices and see a couple of examples of when lattices fail. And notice that we're just going to look at these guys right here. And I got one more example, and we'll see which one of those guys are lattices and how do you tell. Okay, so that'll be it in terms of the rest of the stuff that we've got prepped up in terms of posets. But that is it for today. I'll hang out for a little bit if anybody has questions, and between now and Monday, I'll go and put together the extra resources that you guys requested up on Canvas as well.